You know him as NxGTR. He is a Kaggle master, a kernels expert, and a discussion grandmaster. He's really helpful on the forums, and you get the sense that he's always just describing exactly what we're thinking, right? I don't know if this is a warning or a call out, but as you're walking through these San Francisco streets, look for the brand new yellow Corvette. He's definitely not just a random guy from Instacart. It's Carlos Huertas.
This is super tall. How does this thing work? Okay, hello everyone. Can you hear me? The talk I'm going to give today, it's about dimensionality reduction. It's going to be very practical. I don't want to go like it's super deep in some stuff. I don't even understand some of that yet, to be honest. So if you are on Kaggle, you probably have seen my picture. I'm the random guy with some glasses. I work for Instacart here in San Francisco, and shameless plug, we are hiring if anyone's interested. So I want to start with a brief introduction of what feature selection is, dimensionality reduction in general, and then we are going to see some experiments and something like beyond feature selection, what's next and what can be applied in like in real life. I'm going to try to do this talk like part of what applies to Kaggle and what can be applied to real life, because I mean, I love Kaggle, but I believe that at some point it diverged from real life, and some of the things that you might find useful in Kaggle, it's really not a good idea for real life. So one of the main things that at least myself find when I was starting with data scientists is, are more features better? Is that a good thing? Should I just be getting more and more and more and more stuff? And it's kind of tricky. This is a very famous data set, the iris data set. And I start first plotting on 1 dimension, then 2 dimensions, 3 dimensions. And at some point, it seems to be like you have a better sense of how the data is distributed and how the different classes play together. And you can, well, it's very hard to see like a 4 dimensions and 5 dimensions, that kind of stuff. But I stop at a 3. And the main question will be, well, should I keep just getting more and more and more? And the answer is it's not that easy. I will say it is true. Get more, but that only applies if you are really getting like novel information from those features, which is going to be, in real life, it's going to be very hard that applies, that all your features or your new features are actually contributing like new information. And there's also the no free lunch thing, which means that there's always a price you will pay, either now, either a production, prediction time. There's always a price that you will pay. The only thing that you can pick, I will say, it's how expensive is that going to be, and where in the process you are going to pay that price. This topic is nothing new. It's a very old topic, 1957 probably. People start to analyze this. So we have this phenomenon called information explosion, which talks pretty much about how the rate of information grows much faster than our rate or capability of analyze all of that data. And we end up with this analysis gap. And people start to come up with ideas, how can I reduce my feature space with the data that I collect and still kind of make it work for my algorithms? One of the main questions will be, let's say if I have 100 features, which will be the best set of features that I want to use in my model. Maybe it's not the 100, maybe it's 50, 25, 30, but coming with that number, it's non-trivial. And of course, if I have like unlimited power, I can just write all of those possible combinations, and I will find the best set, right? That kind of works when you have a very small set of features, because it grows very fast. So if you have 4 features, then you have to explore 15 different subsets of possible combinations of your feature space. But well, good luck doing that for 100 features. It's going to take a long time. So you want to reach that best setup of features. And if you have used scikit-learn, which is very popular, you will notice that it's one of the main, let's say, areas that it tries to cover. It's called under the dimensionality reduction. So it provides you with already like a built-in tools for doing this sort of task. And what I've seen, the two main approaches that you will see there, it's feature extraction and feature selection. Both will reduce the dimensionality of your data, but they work in a very different way. And when you pick one or the other, it really depends on what your goal is. Feature extraction technique will pretty much take your original space, and it's going to transform that and give you new features. Usually, it's a lower number, so it's easy to work with. And opposite to feature selection, it's going to take your original space. It's going to pick a couple of those, and it's going to give you a reduced set that you work on. I'm going to dive a little bit deeper in a second. These are, I would say, the most common techniques that you will see. They are available in Scikit-learn, and you will see it very, very popular on Kaggle. SVD, you will see, I would say, mainly on text competitions, where people start to create features such as a bag of words, which you will end up with a massive amount of binary features that you probably want to condense in a couple of vectors, and then you train your models on those vectors instead of the huge matrix that you had before. Then it's a super famous PCA. It has some advantages and disadvantages depending on what you want to do. One of the things that I like is that it works on the covariance metric. So it has some very nice parameters that you can tune about the variance that you want to explain, and it can give you the numbers of vectors that you need to. So the number of, this is going to be your new feature space. It's not non-trivial how to pick those, like how many vectors I want. So 10, 15, 20. PCA will be easier to pick that number. But there's a tricky thing with this. So this reduction of transforming your original space into these new vectors, it's going to happen in the latent space. So who is going to get the benefit of this? I will say it's your algorithm. The algorithm that you're going to train on is going to see, let's say, 20 vectors instead of the original 500 features. The problem with that is, so when you try to put this in production, it's going to work in a system, you will still need your 500 features. Next time you need to make a prediction because you need to recreate those vectors again. So really, for the human, I will say, the cost of like feature storage or your server, that kind of stuff, well, you didn't really have much of a reduction. You still need to, if those features that you were using to build the vectors are expensive, either in terms of money because you maybe need to buy some data, or in terms of computing power because you need to collect that somewhere, well, that didn't change. You will still need to collect all those features before you can create the vectors. I'm not going to dive deeper into this topic because I moved to the other one, which is the one that I want to talk about, which is feature selection instead. The idea is very simple. Yeah, if you are wondering why did I pick that, it's because it's the SF thing. The idea is very simple. You start with all your features, and the question that you really want to answer is, what will be the best subset of those features that will help me to build a model? And then, well, if everything goes well, then you will end up with a reduced set of features that hopefully is going to perform better, or at least it's going to give you other sort of benefits in the process. Here are some of the advantages that you can expect from feature selection. Some fields, like fintech industry, you have to pass a lot of regulations when you build a model. So it's not as simple as that you can just stack like 500 features and then just put it into production. There are a lot of regulations that you need to pass. So you need to explain your model and being able to see what's happening there. So these models are simpler to explain. As you can guess, it's usually simple to explain, let's say, a model that uses 20 features instead of 5,000. Also, obviously, it's faster to train, and prediction also happens faster, not only because of there are less computations to be done, but also, let's say, bandwidth on the network if you need to transfer your features. All of that gets reduced because now you're using a smaller sample. That is also the curse of dimensionality. We talked about many other issues that might arise when you have so many features. Your algorithm may not even perform well. You might overfeed. There are many issues that you will get. I put a K on those last two ones because I believe are the most popular for the Kaggle context. It's one, it's overfitting, so you can help yourself by reducing your feature space to deal with overfitting. You will build a simpler model that is easier to generalize, so you will rank higher on the leaderboard, hopefully. And you can also use this to improve your ensembles. If your idea is maybe, I don't know, build 10 different models just to fight for that last digit in the leaderboard, this will be a good option for you. You can uncorrelate your models by using different feature selection techniques. So each of your models work in a different sample. And then you can ensemble together. And you will usually get a better result. I'm going to show examples later. But yeah, I want to talk about some of the advantage that you might not see in Kaggle, because you don't have to worry about that. You just deploy your model, then you pretty much don't care what happened after that. At least I don't care. But it's important if you want to apply this in real life, because if you have to maintain this later, then it becomes a problem for you. And here's some comparison about what applies there and what might not apply in real life. Usually, what I've seen for most Kaggle competition, someone already formulated the problem for you and build the data set, which is a huge amount of work. And that, I believe, simplifies a lot of the approaches that we take on Kaggle. Another thing, it's code maintainability. So you probably don't care in Kaggle. You can just build like 100 models stacking, and then just deploy that and hope for the best, right? But in real life, you might be wondering what is going to happen after that. Who is going to maintain that code? How hard is it going to be? That changes a little bit the game. You might be able to sacrifice some performance for the sake of being able to sleep instead of being on call and the model broken and that kind of stuff. There comes the server cost, which is related with the prediction speed, the amount of hardware that you will need to build a more complex problem. I talked already about the cost of the features. Some might be very expensive, like the FICO score and that kind of like a fintech information. It's very hard to, it's very expensive to get. And if you find that you can build your model without those features, you can save a lot of money. And I want to talk about a little bit of difference between Kaggle and real life. And I want to pause this example of this is a competition that I did 3 years ago. I did pretty bad. So if you have participated in Kaggle competition, you will know that there's a public and private leaderboard. The idea of the public is that you can't really overfit much, because you will be evaluated in a different set anyway at the end. So I was doing pretty well. I think I was like 20 and 19 place on the public, and I was like, oh yeah, I might win this thing. Then when they released the results, I dropped like 1,600 places. Like, but I believe it's not because I did bad, but I believe it's like kind of in the random zone. If you check the scores, I was like a 0.002 away, like from the goal section. This was a metric, it was AUC. And I still feel that there's some divergence between Kaggle and real life. So this is what I mean when you might be in Kaggle trying a lot of different things, fighting for the last digit, for that 0.002 that might compromise your solution, and you might end up maybe not with the most optimal solution, like for real life. So coming back to the feature selection thing and all this stuff, one of the main things that I've seen people talking about when I talk about this topic, it's they ask the question, which I believe it's a very legit question, is aren't decision trees supposed to be kind of built-in feature selection? Because if we think about how they work, it's like, well, they go through all the features and test which one is going to give me the most gain. And that kind of sounds like feature selection, because it's going to start to pick the best features. And hopefully at the end, you will end up with the non-useful features being discarded or not used at all. The argument that I want to play instead is that, and the reason I put that clock in there is because a broken clock, it's still right twice a day, right? So the thing is, when you start to play with your data, it is possible that at some point in the process, one small sample set just happened to be split the best with one of the noisy features. It might happen. And that means that your model is going to rely on that noisy feature, which you probably don't want that. But don't believe me, I'm usually wrong. So that I run some experiments to show you how this it's actually happening. So one of the questions is, do I really need feature selection if I have these amazing tools like XGBoost, like GBM, that kind of stuff, that are decision trees, so they are supposed to be built-in feature selection, kind of. So I run this experiment. That's a very simple code. I'm going to share this slide so you can replicate if you want. I use this built-in function, which is inside keylearn. It's going to pretty much generate a fake synthetic data set where I have full control of the type of features that I want to create. And the features are sorted in a specific way, so I have access to the ground truth of what is noise and what is actual useful features. In this case, I create 10K samples, total space of 100 features, and I know only the first 5 of them are actually useful. The other 95 are complete noise. Then I built an XGBoost model, and I plot the feature importance. What I was expecting will be the first 5 features to get all of that, and then the remaining 95 get nothing, right? That will be the best case. As you can see, well, that is not the case. It is true that you can see, I don't know if you can see the numbers, but the first 5 actually get like most of the importance, which is what we will expect. We knew that the first 5 were useful and the other were complete noise. But you can also see the other features like, I think, 72, 83, and that kind of stuff. They also got some importance, and they were pure noise. And of course, this is just like a toy example. But in real life, it's not that easy to know which one of those features really matter and which of them were like pure noise, and they just happen to be useful at that particular split. You can also get a lot of benefits of performance. I put it here. Without feature selection, I think I got 0.89 AUC, and after the feature selection, that means only with 5 features, it jumped to 92. It's kind of expected because this experiment is just a little bit biased towards this problem because I created 95 features that are noise. But the point I'm trying to make is that in real life or even in some Kaggle competitions, you might not know which one is the right set that might give you the best performance. And scikit-learn already comes with many options for you to use. Some of those are very simple, like univariate analysis, variance threshold. If you have a constant feature, you probably don't want to put it there. We have the F-test, which is the ANOVA test within your classes. RFE, which is one of my favorite ones. It is kind of slow, but it usually gives you good results. Recursive feature elimination is a very simple process. You pretty much define like a step size, which is the number of features you want to move. Let's say we have 100 features, and we select a step size of 5. That means I'm going to train the model with 100 features. I'm going to drop those 5 at the bottom. I'm going to retrain again, and I'm going to keep dropping the 5 at the bottom until I see the performance starts to degrade. That means I'm going to end up with, hopefully, the best set of features, and the other discarded. There we also have another option, which is a select from model, which you pretty much train a model, usually a linear model or a tree-based model, and then you have access to the feature importance of those techniques, and that helps you to select the number of features that you want to use. Of course, this can be a little bit biased, because if you build a decision tree model as your selector for feature selection, that particular set of features might work for that particular type of model, but might not be very useful for, let's say, a neural network. If you use RFE, you need to plug some specific algorithm. So you could repeat RFE with each of your particular learning algorithms that you plan to build, and then you will probably end up with a very different set of features for each of those. Beyond scikit-learn, I didn't want to just focus on scikit-learn because that's probably very popular and maybe you already know all of that. So I want to integrate like something new, might not be super new, but these are some of techniques that I've used in the past for some of the Kaggle competitions. One is a Reallife, and the thing that I like about this one, it's a filter method. So that means no classifier is being used on that decision of which features are useful. The idea, it's very simple. So you map your data, and then you find what it's called the near hit and near miss, which is pretty much just look for a sample that it's within your same class, and look how different or similar you are to that one. And then you look for the other sample that it's not your class, and of course you want it to be very different in the terms of the feature values that you will get. And then you can compute the distance, and then you get some sort of importance. The idea, it's you want similar samples from the same class to be similar in the distribution of your features, and samples that are from the different class to be, of course, like as different as possible. And that way you can rank all your features, and then you can have a sense of how important are these feature sets. The good thing is, as you can see there, here I'm not using a decision tree or neural network or anything. I'm just working on the data itself. This is what makes a filter model. So this kind of methodology will help you if you really want to just run one time and use this feature space for all of your algorithms. That will work. Instead of you use things like RFE, where you need to plug one classifier. Let's say I want to use RFE with decision tree. Well, that subset of features might not be as useful for other models. There's another popular algorithm, the Boruta one. The idea, it's interesting. You pretty much create like a shadow features, which are like a randomized features based on your original space, trying to come up with the idea of how important my randomized feature is. You always want your features, your real features, to be more important than your best randomized feature. This might be very tricky in some cases. Let me show you one of a real example. I was working in Instacart, and as part of the process, at some point we get some scores. I can't tell what kind of score is that, but at some point we get some scores from the customers, and the data is very sparse. We build a model, and we saw that the score was very powerful for that feature. I was like, oh, well, this might be more interesting than we thought. So we run more testing. So we actually randomized that feature within, it was kind of sparse, so we only randomized within the samples that had value, and the performance remained the same. So it was still a very powerful feature, even after some randomization. So what we found, it was the actual value of the feature was totally irrelevant, and it was only the presence or not of the feature itself, which led us to actually get into the product itself and come back and see what was actually happening. It was just a proxy for something else. So we have to be like kind of careful how we pick the features, because they might mean a different thing that they were intended. I have another examples later. But that's kind of the idea behind Boruta. I actually just discovered this specific package because Boruta is the algorithm, right? But you can have many implementations. And I just found by doing this presentation, this new package, I've used in the past Boruta using random forest as a main classifier. And it's kind of slow. But someone created this Boruta version with XGBoost. They call it Boost Ruta or something like that. And it's super fast. I would recommend it if you want to do like very simple feature selection, because this will run super fast. And it will give you usually very good results, at least if you plan to build NxGTR anyway after this subset. Now that we're talking about the different options that we might have for feature selection, here are some of the characteristics that we are going to find between those, and that might help us to decide which one suits my needs the best. So we can see that we can classify those within the feature space, which is how they work with the data. They're doing just univariate analysis, just taking one feature at a time and looking at it, or they look for more interactions, trying to assess the overall contribution of the feature, with the presence of all the features. We can see about the direction, which is how the features are being selected. If you go forward direction, that means you start with 0 features. You start to keep adding one at a time or one step at a size, one step at a time. That means maybe 5 features, 10, then go 15. Or you can go the opposite way, which is backwards, like RFE. So you start all your feature space, and you start to remove. You can see we can classify those regarding the output as well. Some algorithms will only give you a ranking of the features, which means that you still have another way to go, which is, well, where do you set up the cutoff, right? Because if you start with 200 features, you will get back 200 features ranked by importance. You will still need to do, the next question is, oh, OK, well, where do I set the cutoff? Some other techniques will give you just an actual subset that you can just subsample your data and then move on. In terms of the design, I talked, I think, a little bit before. We have the 2 main approaches: the filter approach, which works independent of classifiers. It just works on the data itself. And we have the wrapper approach, which requires a classifier, like such as RFE. You need a classifier to help you to guide that search. This is a continuation of the experiment that I was showing before, where I created this fake data set. And the red bar represents the performance that I got just using all the features. And then different feature selection techniques that I use and how I was able to improve the performance. This is like the reason I like this topic that much is because it usually leads to a win-win situation, because you get better performance using less features. So it's a faster model, cheaper to compute, maybe cheaper to maintain, and it performs better. So that seems like a win-win to me. But I want to show, like, does this really work? Is it something that can be applied? Sometimes when I read papers, it looks amazing, and then when I try it, it just doesn't work. So I picked 2 past competitions, so you can go and try it yourself. I picked these ones because they had like a lot of features, kind of, 133 one, and then 290 the other one, like a kind of a decent sample size. And I'm going to apply these techniques and show to you what happened. You might see some odd results, and this might be the reason I don't see this topic of feature selection that popular in Kaggle, because it has some trade-offs that I will explain in a moment. I didn't do anything fancy in terms of feature engineering, which to me is the most important part, how you prepare your data. So by the time you build your model, I will say you are pretty much done, or you should be done in terms of your project. Most of the time, I think for Kaggle competitions, I probably spend 90% of my time playing with the data, then only 10% building a model or doing cross-validation, all that kind of stuff. I didn't do any of that here because I didn't want to deviate from this thing. So I just took the data as is, so you can easily replicate these experiments. I just took the data as is. The only thing I did was one hot encode the categorical features. And that's it. I tried to don't tune the model that much. I only play with the depth. And this is the kind of my cross-validation with different techniques. I think it's a very good time to talk about, like the previous talk about the k-fold. You are wondering, how did I pick the k here? I'm usually very lazy with this kind of stuff, so I picked 2 just because it runs faster. And that's it. I didn't do any like scientific stuff. It just picked 2. It kind of worked. But usually for most of my Kaggle competitions, I go even worse, and I just pick 1. Just hope for the best. The reason is, as I mentioned before, I spent like 90% of my time playing with the data and building features and trying to understand the problem. So with the 10% that I have left, I have to go like very fast and then just go as simple as I can. This might not be very scientific, but one of the reasons I usually go this approach is the way I see the problem is if I happen to, let's say, include the target variable as one of my features. I know it's dumb, but just bear with me. If I happen to do that, what is going to happen is that it doesn't matter what I do, I'm always going to get like a perfect result, right? It's going to be amazing. So the way I see this is the better I prepare my data and create my features, the less I have to worry about this cross-validation thing. That's the way I see it. It kind of works. It's like a lazy approach, but that's the way I like to handle these competitions. So here's the results. I did a public and private scores for these competitions. And you might notice something a little bit off, because I've been talking about how amazing feature selection is and how it can help you. Then I show you a plot with where you can actually drop your performance by using feature selection. So that's kind of okay, what's happening here, right? We see this is it was log loss, so lower is better. And you can see the first plot, which is the full feature set, it actually performs slightly better. So we end up with 253 features, and I use extra trees with select from model from scikit-learn, the Veruta package, and the Reallife algorithm. And the number that you see below is the number of features that were selected from the original space. So in Kaggle, you usually just fight for those couple last digits in the leaderboard, and you really want something that helps you that, right? In real life, I usually personally have sacrificed performance in the sake of getting something else back. If you look at the numbers, they are not that wildly different. In Kaggle, this is going to be huge, right? You're going to be maybe 200 places down by using, let's say, 67 features instead of the 253 that you had at the beginning. But if you look at it, it can help you with other things. It can help you to understand the problem better. Maybe it can guide you to look for some sources of data based on this feature selection technique. I put some example on the second plot, which we can see that we had 19 categorical features total, and the model picked only 16 of them. And we had 112 like continuous values that they meant something. It did only pick 20 of those. And the performance is kind of similar. So that usually tells me a lot. It might help if it doesn't help me on the leaderboard, it might help me to understand where to focus and where to do more feature engineering, or where to just look at it and help me to maybe improve even better, even if I don't end up using feature selection at all. The worst case that it can happen is that you end up building different models using your feature selection technique that individually didn't improve your score, but you can always ensemble and get something in return for the time you spend on that experiment. In this case, of course, these results are not very good in the sense that I didn't do anything fancy. I just took the data as is, and it's gonna be very hard to expect for you to rank very high if you do something as simple. But I can show you that it was possible to improve the performance building feature selection with a model that individually didn't improve, but when you ensemble, you get a better score. I think this one improved 0.001. In real life, I would just drop that. I wouldn't bother to use that. But in Kaggle, I mean, you can see the medals right there in the scores and how close they are. So an improvement of 0.001, it might mean something. I'm going to move to the other competition. I pretty much follow the same idea, so no, I'm not going to repeat this. This one, oh yeah, this is important. So the first one was a classification problem. Again, this is our public competition, so you can just look for the names. You have access to this exact data set, and you can replicate these experiments. This one is regression. And here is what I find very good for you to maybe go grab some papers or try to read more a bit about maybe the feature selection techniques that you would like to use, because you will develop some intuition about what might work and what might not. Of course, if you have a lot of time, you can always experiment and try all of them and figure out which one performs the best. But you usually have some constraint on time, And if you have some understanding of how they might work, you might think ahead, okay, this is not going to be useful. And this is the case for, you can see all the lines at the bottom, they're kind of all together, except for Reallife, which did pretty bad. It's the one on the yellow at the top. But this is a regression problem. So if we remember how it worked, picking the near hit and near miss, it is not that trivial now. Who do I pick, especially for a regression problem? So this algorithm did pretty bad here. But I mean, I will encourage you to read the paper. But it's not. I will say it's not very hard to see how this algorithm was not very suitable for this kind of task. And yeah, I mean, the experiment showed it did pretty bad. This is, again, the results that I had. So we start with 328 features. And we were able to actually improve the performance. We see the Boruta one, 162. You managed to get a better performance with roughly half of the data in terms of your features. We have other options. Well, Reallife did pretty bad, as you can see on the plots. But extra trees also did pretty well. Both of them performing like quite good, I would say. And also, if you see the difference between the public and private, that's also something interesting to notice. They overfit more. The ones that use more features, that you overfit more, you can see that huge difference versus, let's say, extra trees with only 80 features. You kind of keep the same performance, and it kind of it's more stable. Because one thing that is very tricky is, so at the end of the day, I will say it doesn't matter your performance on the public or the private or your cross-validation or whatever the way you want to evaluate your model. What I will say, probably you care is what is going to happen with this model in production in 5 months. Because that's the real thing. Even if you did amazing on your cross-validation, well, then what? So you probably want your model to be as generalizable as possible. And I would say the real test is, OK, put it out there, and 5 months later come back and show me that it was really better. And I usually like to do this approach with the feature selection. It helps me to build more confidence in the model. It's going to be more stable. It might not perform as well as other crazy things, but I can trust it more. Again, and if we go back a little bit to Kaggle, again, worst case, if it didn't work, you can always use it to your ensemble and then just crazy build this kind of stuff and just fight for the last digit if that's your thing. But then I think that's a very legit and interesting question. OK, what if I have multiple feature selection techniques? Both of them kind of work. So which one? Or at what point do I set the cutoff between how much I want to reduce and the performance that I might be willing to lose, that kind of stuff. And I think it's a problem of understanding what you are working on and the trade-offs that you are willing to make. In this specific competition, it was about predicting the house price. But if you look at the target, it was insane, the different houses that you had. Some were like insanely expensive, and some other were like a very small apartment. So the error itself, it was very tricky. So I analyzed those both models that I was trying to decide to see which one do I like the best. So now I was looking at the actual error in terms of money, and I will say both models are pretty bad. So it was, instead of looking at which one is best, I was just looking at which one is less or worse. So I think I will always go, instead of, I personally even like this topic, I don't spend like much time of it, because if I had 8 hours, and I think tomorrow we're going to have like 9 hours for the competition, I personally will spend like probably 7 of those on preparing my data and doing feature engineering. And then I will figure out later about the model. But I want to show some of the kernels. I put the link there. I'm going to show the presentation. People did some feature engineering. And that usually will lead you to better improvement that you can do with feature selection. I think both of them together are very good. But if you have to only pick one, I will go with feature engineering instead, and don't worry about feature selection. There are many things that you can do with feature engineering, trying to understand your data, figure out what should matter, or trying to understand the problem. There are other techniques. I'm not going to dive deeper in this, but you can look for genetic algorithms that help you to build like automatic feature engineering. The problem with that is that those kind of algorithms are going to give you a lot of junk, that are things that means like very little in real life. But if you use both feature engineering, like even if it's automatic, and feature selection, you can come up with a pretty decent solution in a very short amount of time, because you can automate all of this, and then that will help save a lot of time for you. And well, I was looking at something interesting. I was reading the code on that kernel. I posted a link so you can look at it. One thing that it gets interesting when you do, let's say, categorical features, what are you going to do with those? I've seen a lot of people do label encoding, which kind of works for the decision trees. That will work. But if we think about, let's say, going back to the Reallife algorithm, if we remember how it works, well, that is going to mess very bad with it, because now the numbers itself that you use for your label encoding means very little. There's no distance there to compute. So I always use one-hot encoder when I want to do feature selection, because that helped me to move to a different topic, which is like level selection, which I can help to understand which of those levels from the categorical features might matter, and will help me understand better the problem. In this case, I didn't get much of an improvement. Most of the gain from that kernel came from some very specific tricks. So you want to go like very deep into Kaggle, you might want to just look for those tricky things. I'm not going to comment on those, but it's a very well-documented kernel that you probably want to check out. So a little bit beyond feature selections, like, OK, what's next? One question that I've been asked before is, OK, which one is very good? So I can start with that. I would say none of them. It really depends on your problem, your data. I would say use your intuition best. And I want to talk about this real-life case that I had. I was working for this fintech company. We do like underwriting analysis. We build a model to predict who's going to pay a loan back. And this is the feature important that we got. It kind of makes sense, right? So bankruptcy at the top, it makes sense. The income also makes sense. That kind of stuff, it's kind of, OK, I kind of trust this model. Then we got this feature at the top. It was very powerful. It's like, OK, this is interesting. This might lead to some new discoveries. It was like whoa. So, and here is where all your feature selection techniques and all your algorithms, I will say, they will fail, right? They will say, well, this is amazing. And I like to state it this way. The fact that something is statistically important, it doesn't mean it should. There's something off with that phone number 2, which is more important than bankruptcy, that I really don't trust it. And so what happened? And again, none of the feature selection techniques is going to help you with that. It's going to tell you that this is an amazing feature and you should use it. But that's not the case, right? So what happened? This is what happened. So when the company had issues with the customer, they reach out to them asking for a second phone number so they can reach out to them easier later, right? So that was part of the data that was given to us, and of course it helped a lot because I knew that those customers had problems in the past, but that was not really a legit feature. That was not going to work. Then you put this. Then if you do your cross-validation, it's going to look amazing. You're going to put this in production. It's going to crash next day, right? So that's the reason I will use intuition over the feature selection. And that's pretty much for me. Thank you.